Hi all, this video is going to take you through the Level 2 Organic paper for 2019. So question 1, you have to name or draw the particular chemical. So first up, 3-methyl-butanoic acid. First things first, draw the carbon chain. So butanoic acid, but means 4 carbons. That's right, so 1, 2, 3, 4. Anoic acid tells you it's a carboxylic acid. So you need to remember that carboxylic acid is a double bond O and an OH. And then 3-methyl tells us there's a methyl group on the third carbon. So when you have a carboxylic acid, the carboxylic acid, that becomes carbon number 1. And this will be 2 and this will be 3. So this is down here is where the methyl group is going to go. The most common mistake on this one is people putting methyl group here because they counted 1, 2, 3. Once you've drawn on all the functional groups, you can then just add hydrogens to make sure that each carbon has 4 bonds. Alright, next one, you're given the compound, or the molecule, you need to try and name it. So first things first, write the carbon chain. You've got 1, 2, 3, 4, 5 carbons. 5 carbons is pent. And the next thing is to identify the funny things which are attached to the molecule. You've got a CH3, which is a methyl group, and you've got an NH2, which is a amino group or an amine. So this chemical here overall is an amine. The NH2 is the one that takes priority, and because the amine is on the 1, 2, 3rd carbon, it is pentan 3 amine. The last thing we need to name is the methyl group. So we've got methyl, and it's going to be on the 2nd carbon because we want to give it the lowest number. So instead of counting 1, 2, 3 where I did there, because that would make it 4-methyl, we start counting from here and it's 1, 2, 2-methyl. And when we do that, we can still see that the amine group is on the 3rd one. Alright, last up, 1,2-dibromopropane-2-ol. So prop, 3 carbons, 1, 2, 3. 2-ol tells us there's an alcohol on the 2nd carbon. And 1,2-dibromo tells us that we've got 2 bromines, one is on the 1st carbon, one is on the 2nd. So one on the 1st, one on the 2nd, and then you go through and add all your hydrogens. So this one can fit 2 more hydrogens, the middle carbon's already got 4 bonds, and the last one needs 3 hydrogens. Alright, the organic structure of blah has been named incorrectly. Draw the implied structure in the box and explain why it is incorrect. So if you draw it out, hex is 6 carbons, 1, 2, 3, 4, 5, 6. 5 then tells you there's a double bond on the 5th. So you've got 1, 2, 3, 4, 5. So your double bond is on the 5th carbon. 5-bromo tells you there's a bromine on the 5th. 1, 2, 3, 4, so it's on the same place. And 2,2-dimethyl tells you there's methyl groups on the 2nd carbon. And the last step is to go through and add all your H's. Okay, so question says it's named incorrectly, draw it and explain why the original naming is wrong. So there's kind of 2 things. Number 1, the alkene takes number priority. Let's do number priority. So therefore we want to give the alkene the lowest number, not the methyl groups. So that is why it should be hex 1-ene, not hex 5-ene. And the second thing is you name side groups alphabetically. So the bromo basically should come before the methyl because B comes in the alphabet before N. So it should be bromo methyl, or dimethyl, sorry, rather than dimethyl bromo. So the thing that stopped most people getting the merit mark on this one is you didn't actually relate it to the example. You gave the statements of alkene takes priority or side groups alphabetically, but you then didn't link it specifically to the example in this particular question. The last one, give the actual name. So there's 1, 2, 3, 6 carbons. So that's hex, and we want to give the double bond the lowest number, so hex 1-ene. You've got 2 types of functional groups. You've got bromo and you've got methyl. So bromo comes first. It's going to be on the 2nd carbon. So 2-bromo. And then you've got your methyl groups, which are going to be on the 1, 2, 3, 4, 5th carbon. So 5, 5, dimethyl hex 1N. Alright, part C. Draw the three non-cyclic constitutional structural isomers of C4H8 in the boxes below. So a structural isomer, you've got the same number of type of atoms, so 4 carbons and 8 hydrogens, but they're arranged slightly differently. So the simplest thing is if you draw 4 carbons and you count up how many hydrogens you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's got too many hydrogens. So whenever you've got double the amount of hydrogens and carbons, that tells you that there's a double bond in there. So let's just start with the simplest. We put the double bond there. And if you go through and fill out all the hydrogens, you got 1, 2, 3, 4, 5, 6, 7, 8. Cool, so that's one isomer. Next up, just draw the same carbon chain, but move the double bond across one more. Again, if you go through, fill up all your hydrogens. Here's another example. Now, if you tried to do the same thing again, and just move the double bond over across, you'd see that this and A are exactly the same. They're just rotated around 180 degrees. So your next kind of step is to start doing branches. So instead of doing a chain of 4, do a chain of 3 and add in a carbon branch, a methyl group. So we still need a double bond to make sure we've only got 8 hydrogens, and you end up with this molecule here. Circular letter for the isomers A to C drawn, which can exist as geometric isomers. So for geometric isomers you need 2 things. You need a double bond, and you need 2 different groups on each carbon in the double bond. So A, you can't do A because it's got a double bond, but if you look at this carbon, the 2 groups attached to it are the same, so it can't be A. If we look at B, it's got a double bond. This carbon has a hydrogen and CH3. They're different. This carbon has a hydrogen and a CH3. So that one can, because there's 2 different groups on it. And if you look at C, this carbon here in the double bond has 2 hydrogens attached to it, so you can't do it for C either. Alright, heptane is a molecule that can exist as geometric isomers drawn below. You need to name them. So this one here is cis. The way I remember it is cis is very similar to the word same. So because the big groups are on the same side, that's why it's cis. This one here, the big groups are on opposite side, therefore it's trans. Lots of people in your discussions below talked about the hydrogens having to be on the same side or hydrogens on opposite side, but it's not a justification in itself. So explain the requirements. So 2 things, you need a double bond, and what it does is it prevents rotation of atoms around the carbons in the double bond. Okay, most people just said it prevents rotation, but that doesn't actually make sense because that molecule will still be rotating around in the air, it will still be spinning round and round and round. What we're interested in is that this particular group, this particular group here cannot rotate and spin round with the hydrogen here. So that double bond there effectively locks this one up the top, this one down the bottom, this one up the top, that one down the bottom. The molecule as a whole can still rotate, but these particular groups cannot rotate. Okay, so preventive rotation of atoms around the carbons in the double bond. Number 2, I think this is where people did it wrong. People said that you had to have hydrogens on the same side or hydrogens on different sides, but it's not the case. Each carbon in a double bond must have 2 different groups on it. And again, what stopped people here is the question says with reference to the heptane isomers up there. So you actually had to specify what the groups are. So this carbon here has an H in this group here. So C1 has an H or a C4H9 group. And carbon 2, it's got a CH3 and an H group. So you can see that each carbon has 2 different groups attached to it. Alright, on to 2. Acrylonitrile, if that's correct, is the monomer used to form a textile polymer known as Orlon. Draw 3 repeating units for the Orlon polymer in the box below. So the way I approach this is try and draw it a different way. So try and draw it how it would actually look as a polymer. So you draw your double bond, and then you draw a group up above and below of each carbon, and then you just fill in whatever groups you're given. So this one here you're told is CH2, so this carbon has 2 hydrogens on it. This one here has a hydrogen and it has a CN group on it, so a hydrogen and a CN group. Doesn't matter if the CN group goes up rather than down, makes no difference. So draw your 3 repeating units. So this monomer occurs 3 times, all exactly the same. And what happens when polymerization occurs is one of the bonds moves, the double bond moves across to form a new single bond between the carbon. That one moves across, that one moves across. Okay. So what you end up forming, so rub everything out, is new single bonds between all of the monomers. And when we draw 3 repeating units, because it's a polymer, it continues on, so you have to draw kind of a bond that keeps going outwards to the sides. Some people put in square brackets, up to you. So, explain why this process is known as addition polymerization. So it's kind of 2 parts. Addition, if you think back to what an addition reaction is, it's the breaking of a double bond and creating single bonds. So you're breaking the double bond of the monomer and you're creating single bonds between the monomers. Second part is polymerization, is where you join monomers into a big long chain. So join lots of monomers together into a chain. Alright, on to part B. Classify the haloalkanes as primary, secondary, or tertiary using the structures drawn below. So the way you work it out is you find your haloalkane, which is the chlorine, and you look at the carbon that it's attached to, and you count how many carbons that's attached to. So this one here is attached to 1, 2, 3 carbons, therefore it is tertiary. If you look at the carbon that the chlorine is attached to, it's attached to 1, 2, it's secondary. If you look at the carbon that the chlorine is attached to, it's attached to 1, it's a primary. So that's your reason. The carbon that Cl bonded to, it's bonded to 3 other carbons. Alright, big question. When 2-chlorobutanes react with alcoholic potassium hydroxide, 2 reaction products are observed. And you need to justify the type of reaction, including a description, structural formula, and an explanation linking the structure of that to the organic products, including reference to major and minor products. So, whenever you form 2 products, it's because you've either done an addition or an elimination reaction. And what you need to recognize is that when you have alcoholic potassium hydroxide, it's an elimination reaction. As soon as you see alcoholic or concentration, it's elimination. So, type of reaction is elimination, and that is the removal of the Cl and the adjacent hydrogen, so a hydrogen from the carbon next door, and you create a double bond in its place. Right. Now what's interesting about this molecule is it's an asymmetric molecule. The reason why is the groups that are attached to the carbon with the chlorine are different. Groups attached to the C. So if I draw it out, 2-chlorobutane, 1, 2, 3, 4, 2-chloro, you can see that the groups attached to this carbon connected to Cl are different. This one here is going to be a CH3 group, whereas over here you've got a CH2, CH3. So in elimination reaction, what can happen? So number 1, if the chlorine is always going to be removed, if this hydrogen gets removed, you end up forming a double bond there, and you end up forming this particular structure. So it's but1ene. On the other hand, if you take away the chlorine and the hydrogen from the carbon next door, you end up forming a double bond there, and when you do that, you produce this molecule, which is but2ene, which incidentally can also form cis and trans isomers. So your next step is an explanation linking the structure of 2-chlorobutane to the products, including reference to major and minor. So we need to work out which of these two products is the major and which is the minor product. So the rule for working this one out is Zaitsev's rule. Don't worry about the spelling. Some people call it anti-Markovnikov. The easy way of remembering it is the poor get poorer. But in an exam you actually have to write it out the full way. And what the full way is the carbon with the least hydrogens will generally lose hydrogen. So you need to be very specific with our particular example. So if I draw out our molecule properly, and I label our carbons 1, 2, 3, 4, we can see that carbon 1 has 3 H's, while carbon 3 only has 2 H's. Therefore, carbon 3 has less, so we'll normally lose the H. Okay, so that means we're normally going to lose the carbon from this particular one, and when we do that, we form that as the product. Therefore, butene is the major. And on the flip side, if we take away the hydrogen from this one here, we then form but1ene, which is the minor. Just put the names up if you haven't worked it out. 2ene and but1ene. Alright, identify the chemical question. So, you need to be able to identify what type of chemicals you have, and you need to understand certain properties of chemicals. So are they acidic, are they basic, are they soluble, etc. So ethanol, straight away you need to work out is an alcohol. Amine is an amine, which is basic, and pentane, which has a double bond. So outline a procedure to positively identify each liquid using red litmus, acidified dichromate, and broming water. So when you do these questions, you want to do it as a step-by-step method, and you need to make sure that you give both positive and negative results. So if you're given litmus paper, always do litmus paper first because it's really easy. It lets you identify anything that's acidic, like a carboxylic acid, or basic, which is an amine. So add red litmus paper, pentane 1, amine will turn it blue as it's basic. That's your positive result. The other two do nothing. Stays red. That's your negative result. Next up, number 2. Add your dichromate to the remaining 2. And you need to recognise that whenever you use dichromate, it's always used to oxidize an alcohol. So what you'll see is ethanol will oxidize into ethanoic acid. Which is this one there. And you'll get a colour change. Dichromate is orange. And when it reacts, it turns into a greeny blue colour, normally green. Pent1ene, on the other hand, will do nothing. Lots of people thought it might react and form a diol, but that's only permanganate. So permanganate will react with an amine to do that, but it won't do it with dichromate. So what you've got left is your broming water and alkene. So add broming water. The alkene will turn it orange to colourless really quick. And in the process it will form a haloalkane. So what have we got? Pent1ene. So 1, 2, 3, 4, 5, which is a double bond here. And when you add broming water is effectively 2 bromine atoms. So one will go to the left, one will go to the right, and you form this product here, along with all the extra hydrogens scattered around. Right, the final question is a reaction scheme. There's no real easy way to do this. It is a lot of memory. You need to remember the different types of reactions that can take place, and you need to remember what the different reagents or chemicals can actually do. In terms of technique, go through and look at the different reagents and see if something springs to mind. You don't always have to work methodically, so you don't always have to start at the start and then work your way through. Sometimes it can actually help if you go to the end of the schedule and see what you have to try and produce and work your way backwards. But in this particular case, it's just easier to start at the start. So the first chemical that you have is an alkene. We know that because there's a double bond, and we do two different reagents to it. We add H2 and we add HCl. Now, when you think of alkenes, there's only one type of reaction that alkenes do, and that is an addition reaction. So you break the double bond and you add atoms to it. So hydrogen, H2, basically one hydrogen will go there, one hydrogen will go there. So when you redraw it, you get this. Okay, there's no other reaction that an alkene can do with hydrogen. Right, HCl, there's two things that can happen. The hydrogen can go there and the Cl can go there. Alternatively, let's get a different colour, the Cl can go there and the hydrogen can go there. And when you do that, you get two different products. You get either 2 chloropropane or 1 chloropropane. Now, the way to work it out, which one is B and which one is C, is if you look at this chemical here, you can see that the alcohol is on the N carbon. Therefore, B must have the chlorine on the N carbon. Okay, if you put the chlorine on the middle carbon, there's no way that you could then suddenly swap in an OH on the N carbon. And that makes this one here, chlorine on the middle carbon. Alright, reagent X. So to go from a haloalkane to an alcohol, you need to add either potassium hydroxide aqueous or sodium hydroxide aqueous. Basically a base, but you need to specify that it's aqueous. Okay, the reason why is if you use concentrated or alcoholic, it would actually undergo an elimination reaction, and you'd turn the haloalkane into an alkene. Alright, alcohol reactions, whenever you use concentrated sulfuric acid, it's an elimination reaction. So you are taking away the OH and one of the H's from next door and dropping in a double bond. So that will become prop 1N. And I'll draw the hydrogens on just to make sure we've got the correct number of hydrogens. Whenever you see permanganate or dichromate with an alcohol, it's always an oxidation reaction. And in year 12, you'll always turn an alcohol into a carboxylic acid. So it's still got 3 carbons, but now it turns into a double bond O and an OH. Oops, wrong one. Alright, last two things. We start off with an alkene, and if you look at this one here, the difference between this and this one here is the double bond has gone and you've added 2 bromine atoms. So you've undergone an addition reaction, you've added bromine atoms. So to do that, we just add Br2. Okay, over on the right hand side, we've gone from a carboxylic acid to this salt here. And if I draw this out, because that may make it a bit easier for people to see what it is, you've got your propanoate ion and then you've got your sodium ion. So what's happened is your carboxylic acid has reacted, it has donated its proton away, and you're left with the propanoate ion. So because E is an acid, because this is an acid, this one here must be a base. And because we're told that sodium is in it, it must be a sodium base. So you can either have sodium hydroxide or you can have sodium carbonate, so Na2CO3. Alright, so reagent X is potassium hydroxide or sodium hydroxide, reagent Y is Br2, and reagent Z is sodium hydroxide or sodium carbonate. Classify each of the reactions 1 to 4 in the above scheme as one of those. So number 1, because we are breaking a double bond and we're adding atoms to it, it is going to be an addition reaction. Number 2, we're swapping a Cl for an OH. Whenever you swap atoms, it's a substitution. Number 3, you're going from an alcohol to a carboxylic acid, which is oxidation. And number 4, we are mixing an acid and a base, so it is an acid-base reaction or a neutralization reaction. Right, the last page, explain why there are 2 products formed in reaction 1 when you mix alkene with HCl, and justify if compound B is a major or minor product. So if we draw it out, and we add HCl, we can see that the HCl can go in 2 different places. If the H goes there and the Cl goes there, we're going to produce this one. Whereas if the H goes there and the Cl goes there, we are going to produce this one. So 1-chloropropane. So what's important to note is that it is an asymmetric molecule. Okay, there are different groups on each carbon in a double bond. Because of that, it means when you add things you can form different molecules. The rule that we deal with is Markovnikov, and in simple terms, the rich get richer. Again, remember, you can remember that little statement, but you can't just give it because it won't give you any marks. What it actually means is the carbon with most hydrogens will generally gain a hydrogen. And again, you need to be specific. You need to actually relate it to this particular example. So if we label our carbons, carbon 1, carbon 2, carbon 3, carbon 1 has 2 H's, while carbon 2 only has 1 H. Okay, therefore, carbon 1, because it's got more hydrogens, will generally gain the H. So the Cl will go to carbon 2, and that makes 2-chloropropane the major, therefore 1-chloropropane is the minor. Okay. Question, justify if compound B used for reaction 2 is a major or minor. So compound B, if you flick back to the other page, was 1-chloro, therefore 1. This is what we kind of need to stress here, that 1-chloropropane is the minor one. Alright, lucky last, it can sometimes take more than one step to convert one organic compound into another. Complete the scheme by drawing propane 1-ol, and we're trying to convert it into propane 1-amine. So first things first, just draw the chemicals that you know. Propane 1-ol is an alcohol that looks like that. Propane 1-amine looks like that. Now remember, an amine is NH2. So even though the reagent is actually NH3, it's only an NH2 group that you actually put on it. So 2 ways you can go about this. You can start off with the alcohol, and you can try and think what reactions alcohols can do. Alternatively, you can think that we're trying to end up with an amine, and there's only really one way that we know how to create an amine, and that is a substitution reaction from a haloalkane. It's the only way we go through in Year 12 to actually form an amine. So we know that compound M must be a haloalkane, and from here it's just trying to work out what the reagents are. So to go from an alcohol to a haloalkane, different reagents you can do. The one I try and encourage my class to do is SOCl2, but you can also do PCl3 or PCl5. You only need to put 1, so just remember 1. To go from a haloalkane to the amine, you need to add ammonia, and it needs to be alcoholic or concentrated. Okay, if you just write ammonia or ammonia aqueous, it's not going to count. The reason why is because aqueous ammonia contains hydroxide, and you can actually end up doing a substitution reaction and swapping the Cl for an OH. So it needs to be alcoholic or concentrated, which means there's no water around. Alright, that is the end of the organic paper. So hopefully that helps. If you have any further questions, please go ask your teacher or come find me. Cheers.